We are live now, ma'am.
Okay. Good morning and welcome to the third lecture on astrophysics. So we will be doing the physics of radiation from astrophysical objects. I have told you in the last two lectures that the three main in physics ingredients which are used or which are useful for astrophysics consist of the main interaction gravitation, the matter of which the astrophysical objects are made, and finally the radiative processes. By that I mean the processes which give rise to the radiation that we observe or measure, because that's the probe that we are using. So now there are different types of radiation which we receive from the astrophysical objects. This is what you see here on this view graph is a spectrum, the solar spectrum. So you notice that there are two broad features in this two broad features in this spectrum. So there is a continuum which spans over a large range of wavelengths, and that approximately is an approximate black body radiation, which is at a temperature of 5700 Kelvin. But so that would have been a smooth curve, but what you see are also minor dips or sometimes very large dips, and these are absorption lines due to various elements which are in the outer layer of the stellar photosphere, and these are known as the Fraunhofer lines. We'll talk a little bit more about this later in this lecture. So this is one kind of spectrum or observation that we may make. And here is another one where once again, so these are actually the various curves correspond to the spectra of galaxies. So spectra means measuring the energy coming from an object as a function of wavelength, or sometimes it could also be frequency. So now here you see that these are spectra coming from 4 galaxies, and what you once again notice is that there is a broad emission feature which is sort of continuously varies as a function of the wavelength. But then there are also spikes which are more like the spectral lines. So these spikes and there are also spikes which are going downwards, so which are like absorption lines. So you have emission lines and absorption lines, and so the emission lines and the absorption lines, they arise from the matter between the stars. So this is just to give you an overview. Now so basically what astronomers measure or try to understand from astrophysical objects is a spectral distribution, which to put it plainly is a variation of intensity with frequency or wavelength or energy, depending on what which wavelength one is measuring or what is the instrument that is being used to measure. So here you see examples of 4 types of emission. One is an emission line, so which means so these are spectral lines, so which are basically excess or deficiency of radiation at a specific frequency relative to nearby frequencies. What you notice in the first 3 ABC parts of this image, of this figure, is that whatever is the change from the flat line occurs in a very small range for a very small range of frequencies. So these are called spectral lines, where you see either enhancement or decrement of radiation within a very short range of frequencies. And the fourth pattern is what is the continuum, and that is what is the black body continuum for a star. So here the radiation sort of varies smoothly with frequency. There could be a functional form, as we will see, like the black body is Planck's curve, like you have a functional form. One could have emission lines which may or may not be superposed on the continuum, but in order to see absorption lines, you would definitely need to have the continuum. We'll see, because we will discuss how the absorption lines arise. Now, before we try to understand what arises from what, we need to have some formalism set up. So primarily, as I said, that we are trying to measure the radiation which is coming from an astrophysical object. So we need some physical quantities. We need to define some physical quantities using which we will be able to compare between, say, 2 objects. So one basic quantity which we measure is the intensity. So which is the intensity of the radiation, that is the energy which passes through, say, a small element dA during the time dt, so such that the normal to the that area is inclined at an angle theta towards which theta is towards the source, and so at an angle theta, whatever radiation is coming within a small solid angle. Solid angle means the angle that is subtended by the source on the sky, and and within the frequency range. So energy passing through a small area in a small time and at an angle, at a specific angle with the normal to that area, within a small solid angle d omega, and within a frequency range between nu to nu plus d nu, can be written as dE, and then we introduce a term that is called the specific intensity times the frequency interval times the angle, cos of the angle that the area makes with the direction of the radiation, and then the times the area times the solid angle times the time interval during which the measurement is being done. And this is the quantity we have to pay attention to. This is called the specific intensity, and this is what we measure when we use a telescope to observe an astrophysical object. And the units of specific intensity are arcs per second, so energy per unit time, per unit area, per unit solid angle. So this SR is steradian, which is the unit for solid angle, per hertz, which is the per unit frequency interval. Now, so now it is often true that we do not see the if the source is very small, then we cannot make out the between the different points on the source, and in that case, what we see is the total radiation which is coming from the source, which means that so there the solid angle subtended by the source is much smaller than the size of our much smaller than the resolution of our telescope. So what we do is we actually integrate over the entire solid angle. So then, and that we call, so the radiation that we would receive is then the energy, so the energy of that that is at a frequency nu, and that passes through the surface element dA per unit time is then called the flux density. And so this is an integral over the angle over which the radiation is received. So you basically integrate over the solid angle. And the last quantity, and this has been mentioned to you earlier as well, is the luminosity of the source, which gives you the energy radiated per unit time. So it has the units of, you can call it arc per second, it can also be, it is basically watts. So joule per second is watt. So if you consider, so you, and that is, if you, so this if you notice this radiation, the flux density would be per unit area would if it is f nu. Then if you integrate over so this r is the distance of the source from the observer. So then if you integrate over the entire sphere around the source and with the size of the with the radius being equal to the distance to the observer, then this is the total luminosity of the source that we will measure. And so that is, so these are the three quantities which are important and which we will use. Now, next we consider what happens when the radiation from the astrophysical objects come, what happens to it on its way. So it obviously interacts with matter. There would be other material in between. So if you are, say, observing a star, then there could be a gas cloud on its way. Then how does the radiation from the star get modified is what we want to know. So when radiation passes through matter, the first thing that comes to mind is that obviously some of the photons will get absorbed. Some of them will get scattered away from our line of sight so that we will no longer be receiving them, and some of them may be destroyed. So all of these can be clubbed together by using a quantity which is called the absorption coefficient, and we write it as alpha nu. And we will see why. So that is the amount of energy which is removed from the beam, which means the direction in which we are looking, per unit volume, per unit time, per unit frequency interval, per unit solid angle at the frequency nu per unit specific intensity at nu. I read it out, but it will become clearer when I write the equation why alpha nu is all of these. Now, another way of mentioning this, what the absorptive effect of the material in between. So this is a case that we have radiation passing through this material, and then what comes out on this side is what we are trying to measure. So now another way of measuring the describing the absorption effects or the reduction that the material causes to the radiation which is passing through it is written in terms of opacity, which is basically absorption coefficient per unit mass. So this alpha nu has a unit of centimeter inverse, 1 over centimeter, and this one is also, then it is this divided by rho. So then this is basically centimeter square by grams. That's what it means. Okay. So now let's see, but then there are also processes which would add photons, because as you imagine, so this is a gas. So a gas, when it is heated, it actually would also radiate itself, right? I have a star, but I have a gas cloud. If it's hot enough, it will radiate. It also contains a lot of could contain a lot of atoms and molecules which will give out spectral lines. So actually there will be photons which will be also added to this beam of light which I'm passing through the this medium, and so that these emission characteristics are put together in something called the emission coefficient, which is J nu. So which once again is defined like this. So, and we will use this very frequently, like various radiative processes will be described in terms of the emission coefficient. So if I put these two together, then what I can write, I can write the differential change in specific intensity of light as it passes through a cylinder of unit cross section and length ds. So I assume the length of this cylinder is ds, and now for this definition I've used that it is a cylinder of unit cross section. So then the differential change in the specific intensity di nu. So specific intensity, if you recall, is the energy per unit area and per unit everything. So that is the one way of saying it. So this d nu by ds. ds is the distance traveled, and that is, so first of all, this is the effect of the absorption. So this is minus alpha nu I nu. So this is reducing the number of photons, or reducing the intensity of radiation. And since this is per unit, so when I defined alpha nu, it is per unit specific intensity. So you see that, so alpha nu times I nu is the total amount of energy which is removed. And plus J nu is, so because J nu is the amount of energy which is contributed by this gas to the beam, to the intensity that we are considering. Okay, so now, so this particular equation is what is called the radiative transfer equation, and it embodies all that we want to know about what is happening to a radiation which is passing when it interacts with matter. And this helps us to solve the problem of actually finding what was the sources in radiation from the source and also from the intervening matter. And in order to simplify the mathematics, there is there are two other terms which are used. The first one is the source function of the matter. So that is defined as J nu by alpha nu. So as you will realize, the way both J nu and alpha nu have been defined, they are properties of the intervening gas. It's not where the radiation was initially coming from. If it was coming from a star, it's not a property of the star, but it is the property, it's a source function of the gas in between. And that is given as J nu by alpha nu. And secondly, we have the optical depth, so which is defined as an integral of alpha nu over the length. So this is alpha nu, as I said, is an absorption coefficient. It has a unit of per centimeter inverse. So when you integrate it over, so this gives us the optical depth. So these are terminologies, and when I use these variables in the radiative transfer equation, I get a form which looks like di nu, d tau nu, and that is equal to minus I nu plus S nu. This is just simple substitution of these two parameters and these two variables. And when the solution for this looks something like this. Now let us look at what it is. So I nu is the radiation intensity of the radiation which is coming out of this cylinder, where the first term is I nu 0 is the background radiation, which means that if there is a source behind it, the radiation which is coming from the source, and that is attenuated. So e to the power minus tau nu. So tau is a positive quantity, so which means that it decreases the background radiation by this amount. And the second term arises from the cylinder itself, or the dust cloud or the gas cloud itself, where the first term is S nu, what we see is that the emission from the cloud itself is also attenuated by the cloud itself. So it is the remnant that will come out of it. So it is the attenuated background radiation and the self-absorbed emission of the cloud itself. Now we can take one case where, suppose there is no star behind the cloud, we are just seeing a gas cloud, a very hot gas cloud. So then we will just be seeing this portion of the radiation. Now there are two special cases which arises. So because this exponential function always has it's a beautiful function. In that sense, it makes things simpler in the two limits. So if suppose this tau nu is very small, much less than 1, then what we call it, so this would simplify the equation, because then this term becomes just tau nu, so it would be S nu tau nu. And so in such a medium, because this tau is a property of the medium through which the radiation is passing, that is called, then such a medium is called optically thin. And if tau is much greater than 1, then much greater than, yes, this should be much greater than 1, then basically this term becomes 0. So and such a medium is called optically thick. So we will encounter them. And so one thing becomes clear, that as this tau goes up, so now consider the whole equation. If this tau becomes very large, then this term becomes 0, and also this term becomes 0. So what the total radiation that we'll be seeing will just be, the observed intensity will just be S nu. We will have no information about the background radiation. So the background radiation gets fully extinguished. Okay, so now yeah, so let me have, if there are some quick questions, I'll answer them.
Yes, ma'am. So first question is, how do we measure the overall spectrum of the galaxy, since it is made up of so many different bodies?
Yes,
Yeah,
that's a very good question. So we actually have different instruments. Like, so we build what are called photometers or spectrometers, which are sensitive to particular regions in the galaxy, particular frequency regimes, and then we combine them together. No one single there is typically so, or it may be that in the same instrument we will different frequency sensitive parts, and we measure them piecewise, and then we reconstruct the thing. Yeah. Second.
Okay. The next question is, the absorption coefficient, does it have any similarity to the Einstein coefficient?
No. Well, it doesn't have any similarity, but both the absorption coefficient and the emission coefficient, as you see, I'm describing some macroscopic properties, and both of them can be expressed in terms of Einstein coefficients, and that is therein lies the beauty, because, and that comes very smoothly. I won't have time to go into that. That comes very smoothly. So that's how we can relate the macroscopic properties of a medium with the microscopic properties of the constituents of the medium.
Okay, ma'am.
Okay, so let's
that's it for now.
Yeah, let's move forward. Yeah, so now I will tell you what do so where do we expect the continuum spectra to arise from. So let's look at, so there are basically three types of transitions which could give rise to continuum. So continuum, as you remember, is that the radiation is varying smoothly with frequency or wavelength. So one could have a free bound transition, which means that it's a transition of electron from an unbound free state to a bound state with the emission of a photon. So it's a typical case of, say, recombination. You have say ionized or you have ions, and when you have electrons recombining to them, so then basically the difference in energy would go out as a recombination photon. And so now why is this a continuum? Because it can absorb photon. The initial electron could have any energy. So the photons of the levels the photons are not restricted. So that's why the energy of the electrons is not restricted. So there is a continuum of energy. The second thing is bound free transition. So where you have this case of, say, photoelectric effect, where you have energetic photons which get absorbed, and then they give out electrons which are emitted into the continuum of free states. So now the thing is that we know that the electrons can be of any energy, which is because if the energy of the electron will be the energy of the photon minus the work function of the material that we have. But in astrophysics, the primary continuum emission that we see are of the kind which are called the free transition, which means that there are two, so there is no bound on the energy of the incoming particle, or basically the transition is between two continuum states. Like the energies can be there is no discrete energy level. So the emitted or absorbed photons also would be exhibiting continuum. So what I will do next is I will take you through three of the major continuum emission mechanisms which we see in astrophysics. The first and the most common mechanism for emission in astrophysical objects, which are often like the astrophysical objects, as you realize, some of them have very high temperatures, and so there is always or even otherwise there are other reasons why there is a significant fraction of ionized material in the gas, and so it can be it is often we encounter a situation which is an optically thin plasma, and this is a thermal plasma because it is because it is just by the temperature being very high, it is hot enough so that they say the hydrogen would be ionized, and so the constituents would be the protons and electrons. Now this why do I mention hydrogen? Because hydrogen is the most abundant species, so if anything has to be ionized, it will, and if it has to show up in a big manner, then it will primarily be hydrogen. So the main electron contribution will be from the ionized hydrogen. Now these ions and electrons are in approximate thermal equilibrium, hence this emission is a thermal. It represents the temperature of the kinetic energy of the system. And if it is thermal, since it's in thermal equilibrium, the speeds that the particles or the electrons and protons in the plasma have, they follow the Maxwell-Boltzmann distribution. So these are the primary things. Now, what happens in such a case is that the electrons and ions, they are in a free optically thin plasma, so they undergo near collision. Once again, it is similar to the say the galaxy or the stellar collisions, but this is somewhat closer. They come closer, so they close enough so they do not collide head on, but they will come close enough, and both of them being charged, they undergo deflection. And but the thing is that the deflection is due to Coulomb force, and electron being lighter, like less massive, it experiences larger acceleration. So now once you accelerate the charge, then it radiates. So this is a basic say electromagnetism, and I like urge you all to look into your books of electromagnetism, that accelerated charges will always radiate. So so these accelerated electrons, they will radiate the energy, and it is that the radiated energy which we see in the form of what is called the Bremsstrahlung. So this is a German word. It means breaking radiation. So Brems means break, and Strahlung is radiation. And this is a case of free, because if you consider both the electrons and the protons to start with, basically they could be in any energy levels there, because they are not bound. It's a soup of electrons. It's a plasma, right? So the resultant, so for this resultant continuum spectrum, so this is a continuum because there are no discrete levels. So we can write the volume emissivity. So volume emissivity is which term? The J-nu term that I had defined earlier. And here, so this term can be written as, so there is a rigorous derivation. I won't have time to go through that, but this is what it depends on. It depends on Z square, which is the atomic number of the ions. It depends on the number densities of electrons and ions, Ne and Ni, and it depends on the temperature to the power minus half, and also there is an exponential dependence on e to the power h nu by kT. So there is an additional factor, which is the Gaunt factor. This Gaunt factor arises due to the fact that these electrons and protons, basically they are very small particles, and here the derivation is often done using classical approximations, but this is also a standard way of treating quantum systems, that you solve for the classical problem, and then you see what kind of corrections are needed if you had considered the system to be a quantum system, and that is expressed in terms of the Gaunt factor. So now notice basically this is how the volume emissivity is written. So it is watt per meter cube. So this is power per volume per hertz. So that is what is written. So now, if you recall that when we wrote down the so now let us consider an optically thin plasma. So we put Z equal to 1, and the Ni, so that the number density of ions and electrons is equal, because if you consider this hydrogen and singly ionized hydrogen, you will have equal numbers of electrons and protons. And if lambda, capital lambda, be the path along the line of sight. So now recall, why am I saying path along the line of sight? Because I wrote down my equation, the radiative transfer equation. If you have not written it down, let me say it again for you. It was d I nu ds equal to minus alpha nu I nu plus J nu. So di nu ds, so ds is the length was the differential length, and that I'm saying is that the total length is now lambda, and on the right hand side I have minus alpha nu I nu plus j nu. So it would help if you have a piece of paper with you, so just write it down. So j nu, so which means that if so now we have I've said that for the process of thermal Bremsstrahlung, this is the volume emissivity and this is j nu. So if I want to go from j nu to the specific intensity that I would observe, assuming it is optically thin. So what is the assumption? Means that there is the absorptive absorption doesn't play an important role. So I will also, it means that the role of the absorption coefficient is, it can be neglected. So my radiative transfer equation would actually be written as di nu ds equals j nu. So now I can then find out I nu by integrating j nu along the path length, and this is so, and this takes care of the geometry of the thing. So if I do that, so the measured the observed intensity will be 1/4π02 lambda j r dr. And so if I substitute the value of j at this point, I will get something like this. Now next I make the assumption that I have a plasma which has a constant density and the temperature is also constant, so that I can take all of these things out of the integral, and then I just integrate from dr from 0 to lambda, and then I will get an expression. So my observed intensity will be proportional to square of the number density of ions or electrons, and then the length of the path length that through the medium, the temperature raised to -12 and exponential of minus h nu over kt, when nu is the frequency at which this, so this should also have a subscript nu. So I am writing the specific intensity at a particular frequency nu. I have dropped this nu here just for the sake of brevity. Okay, so now let's see what do we, so now if what would astronomers, how would we connect the spectra that we observe with what we have learned just now? This is a theoretical derivation, right? So optical, this just thermal Bremsstrahlung, these are like you use that. Okay, so this is what we will be measuring. So what do we have? We have plotted the frequency, logarithm of the frequency along this direction, along x, and the logarithm of the in the intensity along the y direction. And remember, this is the form of our equation. So now this is the form of I that we have. So now so looking at the functional form, it is sort of intuitively obvious why the curves look like this. Now notice that I have two curves corresponding to two temperatures. So, and of which I have written T2 is greater than T1. Is it possible for me to also justify by looking at this functional form that T2 is greater than T1? I would say yes. Why? Because for low frequencies, for small values of frequencies, in this expression, this term will be extremely small. So the value of, say, the value of the function where mu is extremely small will be primarily determined by T. So considering that I have plasma, so I have the same, I'm going through the same length of the plasma, and is identical. So then the value of this end where it will touch, say, the y-axis, will be determined by the value of T, but it is T to the power -12. So the larger the value of T, the smaller will be the value here of the intensity that we'll see here. Now let's take a look at this turnover kind of thing. That is also very obvious. What we see is that this is an exponential. So beyond a certain point, this will take over, and so then it will cause the drop off. And where will that be dropping off? That where h nu, where this h nu becomes almost equal to kt. So h nu by kt approximately, like going close enough to 1, is where we will see the turnover. Now I will make a statement that when this turnover occurs at a frequency, as I say, h nu by k, where h nu is equal to kt, and most of the power is emitted in this frequency region. So you would wonder, so what is power? Power, naively speaking, could be the area under the curve. And what I am saying here is that the most of the power is emitted in this frequency region. Why do I say that? Remember, this is a logarithmic curve. So the values of mu that I have here, so if they are different, if it is a logarithmic of 10, then actually the absolute values of mu here are much, much smaller than the value of mu here. So if I consider, say delta nu in this region, that number will be far, far larger than the delta nu that I consider here. So although it is flat at this part, it is where the frequency is the maximum and still it sort of maintains its large value, that's where I will see the most power. And how does it help me as an observer? Because I know that given, if I know the temperature, if I assume, okay, I am trying to observe a plasma which has a temperature of say 1,000,000 Kelvin, then I know which wavelength it will be the brightest, and so I will choose my telescope accordingly. So now the other things that very quickly come out of this, the first thing is that one thing we can see is that if we look at, so we can easily determine where the frequency, where this curve becomes takes the value 1 over e of the maximum value that it has, and that is the point B. But what happens at the point B? H nu is equal to kt. So I know the nu, so I can determine T. So I can determine the temperature of the plasma, which gives me such a spectrum very easily by looking at, if I have measured it correctly and I have measured basically the turnover and have data points on both sides of it. So just to not to create any confusion, that when we are measuring, we will not measure the continuous curve, but we will measure different parts of the curve, and then we will reconstruct that how the curve is behaving. But it is important to have data points on either side of the turnover just for that reason. So that said that so now I know that what is the temperature, because I have just equated h nu by kt to 1. So I knew, when I knew where this nu correspond, which nu this corresponds to, I can determine what is the T. Now, if I know the T, now let's go to the lower frequency regime. As I said, at that point, basically this factor becomes very small. So this number, the intensity here is actually, it just depends on n square lambda t to the power minus half. But this t to the t is the same as this curve, right? So I have if I determine the temperature at D, I will already know the temperature at C. So I also know the value of n square lambda for the plasma. So this tells you that by making observations in which I just measure the intensities as a function of frequency, I am able to determine the temperature as well as the say the product, basically a quantity which is a product of the square of the number density and the length into the gas that I am observing, or from which this emission is coming. So this, and now let's just to complete the story, where do we see such plasma? So as I said, I have spoken a bit about the supernovae. We'll talk about them tomorrow as well. So supernovae are basically very violent explosions, and when you have a lot of energy, then something you would actually, because of the very high temperatures, most of the elements get ionized. So you actually create a lot of like ionized material, which is plasma. And one can see these examples of this bremsstrahlung also from coronae of in the vicinity of stars. You know that the stars have a very hot layer outside of them, so that is a plasma which is heated to 10 to the 6th, and it is also seen in somewhat more moderate plasmas which are at temperatures so these are basically just ionized hydrogen regions, and these emissions happen mostly, they emit mostly in the radio wavelengths, and they are at temperatures of 10,000 Kelvin. Okay, so now let me talk about the second emission mechanism. So I will take a break after I do all the emission mechanisms, and then I will answer the question. So now the second emission mechanism, which is also very frequently seen, is known as a synchrotron radiation. You may or may not have heard of the term, but I'm sure you have heard of the term cyclotron radiation. So synchrotron is a relativistic form of it. Now this fantastic or a very nice picture, what does it show? It shows the Crab supernova remnant. If you recall, I just now told you that when a supernova happens, it actually generates or dumps so much energy in its surroundings that it ionizes everything. And this beautiful picture with this very bright picture, it's an optical picture. And what you see in here is actually emission from optical lines, but also you see a lot of filaments. But if you zoomed into the center of it, so this is basically a supernova which happened in our galaxy, and this is the Crab supernova remnant. And at the center of it, there is a neutron star. So now neutron stars, I won't go into the details, but the neutron stars actually emit, or it's a pulsar, basically a pulsating neutron star, a rotating neutron star. The pulsars actually emit electrons, and these electrons, now listen carefully, that these electrons, when they move in the medium which is around them. Now, this, what is there in the medium? Well, of course, there is ionized gas, vast ionized gas, but there is also magnetic field. So magnetic field is actually omnipresent. There, it is seen all over the galaxy in the interstellar medium. The origin of the primordial, like where did the first magnetic field come from, is not very obvious, but we know, we are aware of various regeneration mechanisms, and also magnetic field is seen in the stars, and so it is used. So so this material is also, in addition to the matter, there is also magnetic field lines which are going through it. Now, magnetic field lines, and you have magnetic field and you have electrons. This is a problem that you have done when you have a charged particle moving in an moving in a magnetic field. What happens, the motion of it is that basically it spirals around the magnetic field. Now, once again, when it is spiraling, so these are electrons which are highly energetic, means these are relativistic. So when something is spiraling, it means that it is accelerating as well. And as I said, accelerating charges radiate. So this radiation corresponds to what is known as the synchrotron radiation. Now, these are relativistic electrons. So the radiation that comes out can be observed at very high frequencies or energy, the two are synonymous, which are X-ray and gamma ray, and then they are beamed in the forward direction. That is a relativistic effect. I won't go into the details, because so that's what sort of makes them even brighter. Like, it has the effect of sort of focusing the radiation towards the in the direction. So if you are directly in the line of the motion, then you see them to be like even brighter. And so then, and the other property which is also seen, it exhibits, this radiation exhibits polarization. So now polarization is something we often associate with some orientation, right? So now one thing we understand, if the magnetic field lines are parallel, so if there is a general large scale coherence of the magnetic field directions, then all the electrons will essentially be spiraling in the same direction, right? Because they were all spiraling around the magnetic field lines. And so there will be a coherent emission mechanism which would give rise to polarization. If instead the magnetic fields were randomly oriented, then the electrons, with the polarization of individual electrons, the radiation emitted by individual electrons would also be randomly directed. So the net polarization would have been zero. So this is also evidence that the magnetic field is actually oriented in a, there's a large scale coherence of magnetic field in the directions of magnetic fields in the interstellar medium. Now, just very briefly, similar to the say the case of thermal bremsstrahlung, we also can write down the volume emissivity of a single electron. So now we have multiple electrons in the system, but if we want to write down the volume emissivity of a single electron, then it takes the form nu to the power half e to the power minus mu over mu c, where mu c is called the critical frequency, and it goes as E by mec square whole square times mu g. And mu g is something I'm sure you're familiar with, which is Eb by 2 pi me, which is the cyclotron or gyro frequency. That's why the subscript g. And what does this curve look like? If I plot j nu as a function of mu over mu c, obviously it peaks at mu by mu c, where mu by mu c is equal to 1, and then it sort of drops off very fast, which means that the emitted spectrum of these electrons, say if I consider that I have an electron which has an energy E, the emitted spectrum of this electron will be very sharply peaked near the critical frequency mu c. Now, the other thing to notice is that there's the system that I have. So okay, so I can assume that if I want to observe this electron or the radiation from this electron, I have to build an instrument which will like capture most of the part which is at the frequency mu c. But now consider the system. I do not have a single electron. I have actually multiple electrons. So what I need to do is that, and with a distribution of energy. So if the energy changes, the mu c will also change, because mu c is represented by E by mec square whole square. So, and so it will also change. So I will actually have seen such small curves, and this is exactly what is represented here. So these are the curves which will, so now here now this curve is logarithm of like log plot. So both the frequency and the intensity or the flux are expressed in plotted as logs, and then these multiple curves, they correspond to the emission spectrum of individual electrons that we may see in there. And now now let's go back to a bit more of formalism. So now let's see that, okay, I can say that So, but what do I see? I see some radiation which is coming between this and this frequency. I do not see the individual electrons. But what I can say is that, okay, when I see the radiation between nu and nu plus d nu, they must be coming from electrons which have energies between E and E plus dE, because I know that how the nu c is dependent on E. So, but and also, but what is seen, observed is this kind of a emission profile, continuum emission. And here you notice is that on particularly on the higher frequency side, this is called a power law. Like you can, in the log-log plot, you can fit a straight line where the, which is, so the power law typically looks something like this. So like this, e to the power minus p. So so then means the energy, so whatever is the variable to the power of minus some index. And so the, if I fit a straight line to this, what I get is the index of the power law, because in the log-log regime, that is the slope of this line. Now coming back to the formulation, so now if we consider that if the number of electrons with energy between E and E plus dE is like Ne times dE, is given by this, and that is some factor kappa times e to the power minus p dE, where p is the power law index. So then the net volume emissivity that I will see from all these electrons will go as b to the power p plus 1 by 2 mu to the power minus p minus 1 by 2. So now you see, so this is the form that I am seeing here based on a combination of all these individual forms. So which means that the spectral shape that I'm seeing is determined. So now what is P? What have I assumed P to be? P is the power law index in which describes the distribution of number of electrons as a function of energy. So the spectral shape is determined by the shape of the electron energy spectrum. Now, so if I observe, so now as I say that if I say as an observer, I will be observing this. I will say that okay, this is a straight line. So I have so the observed flux density will be mu to the power alpha, can be written as mu to the power alpha. So that is my observed spectral index. But how is that related to the volume emissivity that I have calculated? So that alpha is equivalent to minus p minus 1 by 2. So I can determine p by measuring alpha. So which means that I am able to derive some properties of the gas which is emitting that synchrotron radiation using just measuring the continuum emission from that gas. So the intensity and the frequency of emission depends on, as I say, that it depends on the strength of the magnetic field and also on the charge energy of the charged particles. And the important thing to notice is that it doesn't depend on temperature. In contrast to the, say, the bremsstrahlung that we talked about, there we always saw that it depended on e to the power minus half into e to the power minus h nu by kt. So there was a strong dependence on temperature, so it was thermal. But synchrotron radiation is, that's why it is called non-thermal. It is independent of the temperature. It depends on the energy of the electrons. And so the last mechanism, which is for which I will just show this diagram because you all are familiar with. This is an optically thick mechanism, radiation, which means what does it mean? So optical thickness arises due to what? That it is multiply absorbed and re-emitted. So you are aware how a blackbody radiation can be generated. It is by multiple reflection with the walls on a container. So basically by doing that, it thermalizes, the radiation thermalizes with itself and also with the matter. So in the astrophysical case, often matter and radiation do not thermalize because there can be a huge difference between the energy of the photons and actually the energy of the electrons. But what definitely happens is that the matter itself thermalizes with itself, and the radiation, then the radiation that comes out of it. So the matter itself, because it is the matter which is emitting the blackbody radiation, that is thermalized. So that is like we can describe the properties of the matter using a single temperature. So the spectrum of such a system would looks like this. This is the Planck's law, and this depends only on the temperature of the emitting body. And you are aware of two very, like I'm sure these are two very common examples. The first one is the cosmic microwave background radiation, which is black body radiation at 2.73 Kelvin, and the other is the stellar spectra. We have been talking about the stellar spectra repeatedly. That so these are basically also the black body radiation, and this is what sort of approximation when h nu becomes much smaller than kt. There we see that the form becomes much simpler, and this is what happens. So it's just proportional to nu squared t. So these are the two regimes regimes. You are aware of this, the Wien's regime and the Rayleigh-Jeans regime. So this is the Rayleigh-Jeans regime, whereas in the Wien's regime, the e to the power minus h nu by kt form of it dominates. Okay, so I will stop here and take questions.
Okay, ma'am, there are a few questions. First one is, can you explain free emission, how it actually happens?
Well, as I said, basically it's a Coulomb interaction between electrons and protons, and so I cannot do I don't have time to do the derivation. So it's you have to calculate like what is the force acting on the electron when it is in the coming fluid, and then calculate what is the acceleration, and then you are aware of Larmor's formula. So then you use that to determine what is the power radiated by an accelerated charge. So it's basically when you accelerate a charge. So please go back and look into the accelerate. I have so for the Zoom users, there is a link on in Moodle with, about this accelerated charges, and for all YouTube users also there is a link. So you just search for radiation from accelerated charges. This is a whole topic by itself. So the main thing I want you to understand is that this happens because the electrons get accelerated and then there is a radiation. And that radiation is the heat wave.
Uh, okay, the next question is, how do we get the term J nu from alpha nu and I nu, the integration that was done? And what is the
Uh,
term lambda represents?
Okay, so the J nu, we never get J nu from alpha nu and I nu. Alpha nu talks about the absorption, and J nu is about the emission. So since I do not have time, this J nu actually comes by when you do the calculations, like what is the power emitted for that free interaction. So that gives me the J nu term, if that's what your question is. And then so now if you say that, so now if you look at, so this was the, as I said, you should have a pen and paper with you when you are sitting in this. So this is the form of the radiative transfer equation. Now look carefully. If I do not have any alpha nu, just say there is no absorption, no radiation is being lost due to absorption, then I have J nu only. So then how would I get I nu? How can I get I nu? If I integrate J nu over ds, and that's exactly what is being done. And so the length over which so now look at the look at the limits of integral. This 0 to lambda. Lambda is the length into the medium from which we are receiving this emission. Okay, so alpha nu is not involved. So because we could neglect alpha nu because we have assumed it to be optically thin. Yes.
Okay, and what the lambda term represents actually?
Well, as I said, it is the length of the column. So if ds is the length along, so you have a cylinder through which radiation is passing. So so it's the depth into that cylinder, that is what. So I say that, okay, it's a lambda centimeters. It is the finite length of the column. That's all the emitting particles, all the electrons in this case, that are located within the length lambda for a a cylinder of unit cross section that I have. They will all be radiating. I will be receiving the radiation from all of them. So it's just the whatever is, so that the term along the line of sight, it means that it has to be along my line of sight, that what is the length that cuts into the source from which I am receiving radiation.
Okay, one last question, ma'am.
Hmm.
Can you repeat how you measure temperature at the point D from the graph?
Okay. Yeah, so point D is where the intensity falls to 1 by E of its maximum value. So if I have measured it here and I have measured it here and here, I know that the max. So this is the flat portion. So this is the maximum value. So which corresponds to this, and then so at this point, this is equal to n square lambda t to the power minus half. This term is close to 1. And but when it becomes 1 by E of it, so as I increase nu, this term becomes larger and larger until this factor becomes -1. This exponent becomes -1. So then then it will be this term into 1 by E, and that is the point D. So when I know that, so now where did that happen? It happened at the frequency nu. So h nu by, so at, which means that this is at the frequency where h nu by kt is equal to 1. So I know which frequency it happened at. I know h, which is these h and k, these are all constants, and so I can determine. Okay,
Okay, I
yeah, I
think we
think
can
I
continue.
go ahead. Yeah.
Yeah. Yes.
Okay, so we just talked about the continue, and then we'll finish off with the other important emission. Well, basically the emission that we receive from astrophysical object. Once again, we see the spectral lines. So actually, these Fraunhofer lines are, I think, is the most wonderful thing that in historically one can say has happened to astrophysics. The thing is, these absorption lines were observed in the spectrum of the sun. So you may be more familiar with this form if you do there's a nice wiki on this. So, but what it also, what people realize, and that's where lies the ingenuity of people, that when you see something so far away and you see some similar thing in your terrestrial laboratories, you are able to correlate. So what happened is that then it also happened that there were a couple of I've forgotten the names of those I'm sorry, the scientists who actually looked into the Bunsen flame, and they actually saw that basically in the gas form of various elements, spectral lines which match exactly with the frequencies that were seen in the frequencies of the absorption lines that were seen in the solar spectrum. So they then sort of uh, uh, they then sort of argued that it must be that those elements are present in the atmosphere of the sun, or means in the photosphere of the sun. So that sort of, that is actually a piece of, I would say, a piece of genius, that to say, to think that even the star also must be having the same elements, and to do it for the first time. Of course, then it went, people did a much more careful work, and one actually could associate the various lines to different kinds of, as you can see, there are some molecules, and then there are some ions, and basically there are quite a few ions, and then also there are so some atoms. So various kinds of, so all of these assignments were done. So this was the first, I would say, the most fascinating thing that happened, and that sort of told us that okay, some of the laboratory spectroscopy that we do could be useful for to study the astrophysical objects as well. So now there are two important concepts. I've been talking about these spectral lines, and I've been talking about them being in emission and absorption, just to give you a quick glance of what we know. So now this emission and absorption, it not only depends on what atoms or molecules we have, but it also depends on the conditions, like the temperature and pressure in which they exist. These spectral lines typically arise from these atoms and molecules undergoing transition. So that's why they are not really like free. They are confined to, in these cases, the atoms and molecules, they are they can exist only in discrete levels. So when they somehow move from a higher energy level to a lower energy level, they have to do it by emitting a photon. And if that photon, if that happens in, say, an astrophysical object, and if that photon manages to leave the system, then we are able to observe it, and that is our spectrum. So now this, and we see the emission lines, we get the emission lines if many atoms go from highly excited state to the lower energy state. And we would see the absorption lines if the if these atoms which are excited to a higher energy state, they can absorb, well, if atoms could be excited to the higher energy state by the absorption of photons. Now just to explain what I mean by that, so suppose this is a bulb. So bulb is emitting a continuum radiation, and then I have a cloud of sodium atoms. So all of you are familiar with the sodium lines in the optics laboratory. So now I have put prisms in three directions. So first of all, if I put a prism here, what happens is that I have the basically I have the bulb. So now I put a prism. So I have split up the light. The white light becomes it splits up into the pure. So I see the continuum spectrum. I have put another prism, so along a line of sight where I am looking only at the sodium atoms. So sodium atoms are obviously excited by the light that is coming to them. So, but this is like a bright hot gas, and what I will see are the lines which correspond to emission lines, which correspond to difference in frequency between two levels of the each of them corresponds to the difference in frequency between two levels in the of the sodium atom. However, when I put a prism here, what I would see is that I would see both the emission. So this is exactly like what we saw for the sun. We would see the continuum emission, but now consider what is happening. So I have the continuum emission, which passes through this cloud. Now, for those frequencies for which the sodium clouds can have so those frequencies which match the energy difference between two sodium atom levels, then they will get absorbed, because by absorbing that radiation, the sodium atom can go from the lower energy state to the higher energy state. But what does it mean to the continuum radiation which was coming towards my direction? It means that those frequencies get removed from the continuum radiation, and that's exactly what I see here. So that gives rise to the absorption line. So basically this is what is written here. So basically, if atoms are excited to a higher energy state through absorption of photons, only photons of energy delta E will be absorbed. So that absorption will just be confined to the delta E, which is the difference in energy between the two concerned levels, if absorbing atoms lie between the observer and the source of photons, and a deficiency of photons at these frequencies will be observed. So this explains why we see in the case of the sun. So the next one explains it more. So basically, if you look, so now you consider this is like our sun, and we consider various lines of sight to this. Lines of sight means I look at it from different directions. So now this is the line of sight we typically have towards our sun, which means that in this case, what is happening? So the photosphere of the sun, that has a large number of elements in ionized as well as some in atomic and some in molecular forms, maybe, or molecular oxygen is seen. So they exist in that there. And so, but then this is the case similar to where you had the bulb here. So this is the bulb, and then you had the thin layer of gas cloud, and you are observing here. So which means that you have, what you are observing here is a star. This flat thing means that I have a continuum, which means you see that it's not zero, it's a raised value, but then only at the positions where, or the frequencies where at which the frequencies which match the energy level differences between two levels, or two atomic levels of the gas here, then I will see the absorption line. Similarly, if I consider that I go through the line of sight B prime, so here, say, suppose many stars actually, because of their so the star, consider the star is rotating like this. So this is the spin axis. So then they actually emit some gas along the equator. It can be ejected. So then I'm observing it. If I observe that ejected gas, that will be similar to the case that if you are looking just at the sodium cloud in the previous view graph. So when I go back, you take a look at these things again. So that is similar to that. So then I will be seeing some emission lines, because then I do not see the continuum anymore. My line of sight doesn't cross the continuum, but it sees only this radiation from these clouds, but they are very faint. And finally, if I no, the rejected gas, it looks something like this, but it's also possible to see another along the line of sight, which is for the chromospheric emission lines. I will leave this on for some time. You can take a look at it later. I won't go into the details, I think. But so what this means is that, say, in order to observe lines close to the stars, emission lines, one actually needs large amount of hot gas, which is illuminated by the star or otherwise, like. So in order to detect that, because you see this hot gas, I can see only very faint lines corresponding to it, but I do see very strong absorption lines, because this emission actually so we won't go into the details now. Okay, so now this is but there you need some exotic phenomena, something like you need an accretion disk, which sort of makes the gas heat up significantly. However, it is much easier to detect the spectral lines in other astrophysics astrophysical objects, particularly like the interstellar medium. And here what we see is that, so because in the interstellar medium the densities are not that high as in the star, but the gas is reasonably hot, and then so there is no, say, as far as such, there could be it's not dominated by the continuum of the star, so the gas is hot enough. And it is, so this is an example of the emission line that is seen towards a very young star forming region. These regions are such massive star forming regions are called hot cores, because of the reason that they also show evidence of a large number of molecules. Trust me, there are a lot of molecules. So this is actually related to the work that like the research that I do work on, and also. So and as we saw earlier that for galaxies also, so this is a sort of, once again, the spectral energy distribution, as it is called, for the Circinus galaxy. Here you see there is a continuum. The continuum here, as we will learn later, it arises due to mainly the dust which is a refractory element. I won't confuse you now. But the spikes that you see, they are the spectral lines. So it's much easier to detect these spectral lines in emission towards this say towards the hot interstellar medium and the galaxies. And the diffuse clouds are typically detected in absorption lines because there it is much easier to detect them. And so finally, just to wrap it up, what are the spectral lines that we are talking about? So we can broadly classify the spectral lines into two categories. One is the permitted lines, which arise from allowed or electric dipole transitions. Just to understand that you can consider or approximate a molecule as or an atom as a dipole. So then you can consider the interaction of the dipole with an electric field, so the radiation field. And so based on so that interaction itself tells you whether it will absorb the radiation or it will and contribute to the radiation. So that interaction, so that's an electric dipole interaction. And when you do it quantum mechanically, then you see that these the transitions are allowed. So there are some things called selection rules, which only allow certain transitions. And so then, but these transitions, when they happen, they happen very quickly. And the typical lifetime of an atom in an excited state is something like 10⁻⁸ seconds. And examples of such things are like vibrational and rotational transitions of molecules or recombination lines. And finally, but what is the difference between permitted and why do I say permitted? So there is another category of lines which we call forbidden lines. So in this case, what happens is transitions are not allowed by a particular selection rule, this electric dipole selection rules, but then they are allowed by a higher level of approximation. It could be magnetic dipole or it could be electric quadrupole. So these are all like things which you will probably learn or have already learned in your atomic and molecular physics courses. But these transitions do happen, but then they happen at a much lower rate. And so which means that the atoms remain in the higher upper state for they have a mean lifetime of between 0.01 to 100 seconds. Contrast this to the 10⁻⁸ second, and these states are called metastable states. Now, what happens in the terrestrial laboratories? In the terrestrial laboratories, we actually have very large number of molecules or atoms, number of particles. So they are always colliding with each other, which is not at all the case in the interstellar medium or for the astrophysical objects, as I've been telling repeatedly. So in the terrestrial laboratories, since or even under best vacuum conditions, the collision time between these atoms is about of the order of 1 second. So which means that if some atom is in one of those metastable states, it will not stay there for this 0.01 to 100 seconds because it will just collide against another atom and come down to the lower level. And as a result, if it comes down collisionally, then there will be no emission of photons. Only if it can come down by using spontaneously, by using spontaneous emission, then only a photon will be emitted, and then the spectral line can be seen. So in the terrestrial laboratories, we typically do not observe such transitions, but in the astrophysical case, they are very frequently seen, and they are actually one of the major cooling lines for the interstellar medium, which helps in structure formation. Okay, I'll stop here. Sorry, I overshot a bit. Okay, let's have a few questions. And yeah.
Yeah, ma'am. So the first question is, how would we estimate lambda in, say, an observed spectrum?
Which lambda? What is the lambda here?
Hello?
Yeah, what is the lambda here?
Ma'am, the lambda that we talked earlier, the length.
Yeah, so as I said, this is it. So as I said, we have an estimate. So looking at the thermal Briggs-Stallone, I said we get an estimate of n squared times lambda. So it tells you about the distance to which we can measure. So typically, it is difficult to measure, but so that's why many things are expressed in terms of something that is called column density, which means the number of atoms or molecules or or whatever is the emitting particles per unit area of a cylinder. So the lambda, yeah, so that's how it is measured. Or
Okay.
if you, the other option is that if you, since say when you look at a star or if you look at a region, you are seeing a 2D projection of it, right? But it's a 3D thing. You can assume that it extends as much along your line of sight as it is across your line of sight. That is the other approximation, well, estimation that.
And one more question. Uh,
Yes,
in synchrotron radiation, how we can say
yes.
that the intensity and frequency of emission uh, are not dependent on temperature? Because as we increase temperature, energy of electrons should also increase.
Yes, the energy of electron will increase, but as we saw, it depends on the power law of the energy. So, so the distribution of electrons, how many electrons we have, what energy, so that will that decides it. So it is the direct dependence on temperature because of the presence of the magnetic field. So it's not directly dependent on the temperature as we see. And also, if the magnetic field were not there, then this emission would not happen. So the dominant factor is not the temperature. You can calculate what will be the change in energy due to the, so what factor, what because this, the heating also depends on something else. So I would leave it at that. It's more complicated than.
Okay, ma'am. Thank you, ma'am.
Okay,
That's it.
okay. So I just wanted to announce, so for the students who are on Zoom, you can still ask questions about lectures 1 and 2 on the Moodle. And students who are on YouTube, you can actually write on the chat for the, say, the next lecture. We will be saving all the chats anyway. And then if it's, even if it's a question from the previous lectures, I will answer them because you have also been receiving the responses for some of the questions. Everybody is asking. We are not distinguishing between YouTube and Zoom students. Okay. So, okay. So thank you so much. Let me just stop sharing and yeah. Okay. So
Thank
I'll
you,
see
ma'am.
you.